Okay, can everyone see my screen?
Yes.
Yes.
Oh, so first things first, Daniel has just said this, so I won't spend too long on it, but if you haven't got the link up on your computer yet, this is the only URL you need to know. All other links can be found there, so do copy paste it into your browser. I believe someone put it in the chat as well. We could do with a note taker for this session. We will later ask for a note taker for the second session, but just for now, if anyone would like to volunteer, it would be really helpful.
You can use the chat to volunteer or send a private message.
Feel free to send a message to any one of me or Daniel or Yuval, or to volunteer on the group chat. And ideally, we would sort of get going with the note taking once we start the discussion. So I would like to introduce Behzad Abdolmaleki, who is going to be giving the talk, which is going to be SoK on lifting transformations for simulation extractable, subversion, and updatable SNARKS. Behzad is currently a junior research fellow in cryptography and a final year PhD student at the University of Tartu. He is supervised by Helga Littmer, and his research interests include zero knowledge, smooth projective hash functions, and lattice-based cryptography. And I'll now pass over to him.
Okay, thank you. Let me just share my slide. Okay, I hope. Okay, can you see my slide? Okay.
Yes.
Okay, very good. Thank you for introduction. I'm gonna today talk about a framework that takes any SNARK as an input and output simulation extractable or non-malleable version of SNARK. And this is a joint work with Sebastian and Daniel from AIT, Austrian Institute of Technology. And I would say that the full version of this work will appear in the CCS 20 this year. So let's have a general outline of the talk and how we can get this new framework. First, we start with some basic definitions of non-interactive zero knowledge and SNARK and subversion and updatable definition, and then we first look at the framework which called OCOCO, which proposed by Cospa et al. In 2015, and this framework actually takes any NISIC and output a black box simulation sound NISIC, and aim to get the UC security property of the NISIC. And then we just first analyze this framework and do some optimization, and we call it OCOCO or optimized version of OCOCO, and then show how you can get subversion zero knowledge from and then we will show how this OCOCO framework output a subversion of a simulation sound subversion SNARK when you have a standard SNARK, a standard subversion SNARK. And then later we will define a new framework which is called LAMUSA, different tools and different ideas, and then we will show how that this new framework returns also subversion updatable SNARK, I mean besides subversion SNARK. So this is the more relaxed version, and you can take any SNARK as an input and get a simulation sound version of that SNARK. Let's have a brief overview of the definition of NISIC in the Common Reference String Model or CRS model. In such a model, actually, there is a trusted third party who shares and an approver and some verifiers, where this trusted party generates a common reference string or CRS and shares it to the others. And later prover aims to give a proof for his claim that he knows a word or for a word which is in the language. And then this proof should be verifiable from some other verifier. And such a construction should satisfy three conditions. The first is correctness, says that honest prover should be able to convince the honest verifier. And soundness says that this honest prover should not be able to, soundness should guarantee that the dishonest prover should not be able to convince the verifier with the word which is not in the language. And zero knowledge, which is the more tricky one, is that it guarantees that the proof of the prover does not reveal any information of his witness. And usually for proving such a statement, we usually imagine that there is a imaginary guide who has access to the chapter of the CRS, but not witness, and can generate a proof which is indistinguishable from the real proof. This talk, we mainly actually work, we are interested to the soundness property, and we want to also make this definition more stronger, that's called simulation sound. We will see in the future, in the next slide, what we mean with that. And later, a special type of music, which is the most, which is the succinct non-interactive zero knowledge, is called SNARK, which by SNARK, we mean that, okay, it has a small size of proof and low verification complexity. And about its history, it started by graph 10, and then there were a lot of versions of it, and finally again ended by graph 16, which at the end the proof contains 3 group elements, which currently this is the most efficient version of the ZK SNARK. And also in another direction, Belar et al. Just studied the NIZIC construction in a subversion setting where, for example, verifier and prover does not need to trust the CRS generator. And they also proved some possibility and impossibility results in a way that you can see in a table actually, but mostly we are interested in the result in the last row and in the last column, means that subversion sound plus subversion ZK. And here we can see that having subversion sound and subversion ZK is impossible, but having subversion ZK plus sound is possible. And we will see that in the next slide. This is the, for example, in the most efficient SNARK, for example, by the SNARK by graph is in the CRS model, and later Abdolmaleki et al. In Asia Crypt 17 and also Fuchs in PKC 18. They just implemented the CRS in the subversion setting where the verifier, where the prover does not need to trust the CRS generator. So from prover point of view, verifier and CRS generator can communicate to each other. So they just they relaxed the SNARK in such a setting. And just recently, there is an Grass et al. Proposed a new notion that's called updatable SNARK. That in such a setting, actually, this is the more relaxed version where neither prover nor verifier does not need to trust the CRS generator as long as verifier at least does one of the updating procedure. And here I would say that the updatable SNARK can easily, satisfy the subversion property as well. So this is the more relaxed version. The trust here is interested to mostly talk about a strong notion which is called simulation extractability in the soundness side. But first, we start with the definition of the soundness and knowledge sound, and have an overview how we can get knowledge sound from the sound. Here, there are two ways. The first way is called black box way, which in such a way, we can see that beside the statement, I mean, a statement extended with the way that one needs to encrypt the witness and also give a proof that he knows the witness that is in the language. And to this aim, one needs to extend the CRS with a public key of gamma. Gamma is a public key encryption, CP public key encryption. And then prover needs to, in addition the proof, he needs to also encrypt his witness and prove that they are compatible, that they are consistent. And in that case, also one can put the secret key of the public key as a extraction trapdoor in a way that then knowledge extractor, for example, can, by having this trapdoor, can extract the knowledge. Can extract the witness. For example, in case of encryption, he can easily decrypt the encryption and get the witness. So this is the more, the stronger version that called knowledge sound. Another way to get the knowledge sound is non-black box way, which instead of encrypting the witness, one can rely on some non-falsible assumption. And I would say that the all SNARK version are based on this non-black box way, in a way, and this is the reason that actually their proof is very short. Otherwise, it would count also the encryption of the witness. And let's have a look at the what we mean with the simulation sound here. By the simulation sound, for example, in the real world, we can see that prover, a malicious prover or an adversary can see many different proofs. So he might be able to give a proof for a different proof for the same board, or a different proof for a different board. I mean, these all are the possible ways for the adversary. And so for the proof, for the definition of simulation sound, we should we say that by giving the query, the Oracle query access to the malicious prover, or let's say adversary, he should not be able to generate such a proof of P prime either for board X or for a different board X. So we called it weak simulation sound for when the proof pi is for the same board X, or it is the a strong simulation sound. So this issue also is in the signature and other things, I guess. And and there are a construction by Canetti, by Gross 2006, and also I don't recall the name of the author. That they propose how one can get from soundness to the simulation sound property in a way that one can extend the CRS with a new public key, which is a signature, a public key of the signature. And then in the prover side, prover needs to generate a new KP of a one-time signature scheme, and then extend the statement with the following. And then after generating the proof, he can sign the proof with the secret key that he locally generated. And about the zero knowledge proof, one can put this secret key of the signature as a simulation trapdoor. So in the proof, the simulator can give a proof for the second part of the OR, and the prover can give a proof for the first part of the OR. So, and just recently in 2015, Kospa et al. Proposed a new framework which called composable zero knowledge compact zero knowledge, or in short, it is COCO, which actually this framework gets any NISIC as an input and outputs a black box simulation sound version of this NIS. And the main goal of the paper was to achieve UC security for the NISIC. So they just extended the statement with the following way, which add the encryption of the witness just to get the black box extraction, and then the original is the statement of the NIS, and then two new cases, mu and rho, which is a PRF of some locally public key generated by the prover and the commitment. And here by the red color, I mean, they are secret. So some of them are known by the real prover, and some of them, for example, like at S and R0, are known by the simulator in the zero knowledge proof. And prover needs to run to give a proof for the new language, and then sign everything with the SK1, which is the secret key of the signature that's generated by the prover locally. And then one can see that to get such a construction, one can extend the CRS with the rho, which is a commitment, and the public key of the encryption. And then the chapter of for the simulating would be S and R0, which simulator gets it to simulate the proof because he doesn't know the witness. And for achieving the extraction, because we want to get the simulation sound, simulation extractable sound or knowledge sound. So by having the secret key of the encryption, the public encryption, one can extract the witness. And also they implemented their construction with by assuming the public key as RSA and using the deterministic ECDSA as a one-time signature. And also Bagri 19 says that one alternative would be Boner Boy, or for the use of the signature, or one can use also Grass one-time signature. And they used also SHA-256 instead of PRF and committing. And they prove the commitment or the security of the construction is in the random Oracle model. Actually, this was one of the disadvantages. And now the question was that how to commit the PRF key while retaining provable security. To this end, actually, our first result is we just modified the COCO and called it OCOCO in a way that we use the fixed value key binding PRF, which was proposed by Canetti et al. And Fishling, which the reason that we used actually that case, we use this key binding PRF and replace it to the commitment scheme. And just a short definition of this key binding PRF. It says that, okay, for a PRF with key S and some special value of choice beta, it is hard to find the S0 such that Fs by evaluation in beta is equal to F0 evaluation in the same beta, and S0 is not equal to S. And why we need such a, key fixed value key binding PRF instead of commitment, and not first we observe that, okay, the standard PRF might not imply the binding property of the commitment, but fixed value binding PRF can satisfy such a property, such binding property for which is important in case you have a commitment. And so in OCOCO, you need to extend the statement with the following way, which the only different the last part is the commitment. And we also analyzed the OCOCO with the different local symmetric primitive, and you can see here. So, and here you can see that, for example, for COCO, they use both for PRF and commitment, the HMAC PRF, and also a hash commitment for the commitment. But since we remove this hash commitment, we use for both cases PRF. So, and we analyze it with different kind of things, and you can see here. And the second result of this work is to define a new framework, which is called the LAMUSA, which can convert any SNARK to the simulation sound version of that SNARK. By any SNARK, I mean a standard SNARK, Subversion, or Updatable. Just very briefly, so far we know that, okay, from the SNARK, there are two versions of SNARK. Let's say Updatable, for example, is started by Grass et al. In 18, and a Subversion version of SNARK. And by having COCOCO, or better, non-black box COCO, which was proposed by Barger in 19, and also the DS19 framework, one can get simulation sound extractable version of those SNARK. But they can just provide a standard. They can take as an input a standard SNARK or Subversion SNARK. So, but LAMUSA construction can transfer any kind of SNARK to the simulation extractable version of that. So. We built actually LAMUSA based on two important cases. The first one is updatable signature. We defined a new notion of signature called it updatable. And also this is run with the compiler of DS19, I mean, with Euler and Salaman 19. And first we will have a look at this compiler, and then have a very brief on the updatable signature and see how we can build LAMUSA. DS compiler mainly is based on the Key-homomorphic signature. And so before explaining the compiler, I would just have a brief explanation on the Key-homomorphic signature. In such a setting, actually, there is a homomorphism between a secret key and a public key, and we call it, let's say that function be mu that transfer any from the secret to the public space. For example, in the DLOG setting, this mu can be exponentiation in a way that it gets something secret and compute g to the power x. And signature, actually this Key-homomorphic signature can be adopted from pk to pk0 if one knows the sk0 and the real sk. So it means that actually we will see that this notion of the Key-homomorphic signature will lead us to get updatable signature. For example, for such a, as an example, you can think about Schnorr or BLS or any other signature that satisfies it. And now let's start to see what is the compiler of DS19. In their compiler, similar to COCO, they also extended their CRS with the, before I would say that this compiler gets any NIZIC, any knowledge NIZIC as the input and output simulation extractable of this NIZIC. And this, to this aim, they just extended the public key, extended the CRS by adding the new public key P key, which is the public key of the homomorphic unforgeable chosen message attack signature. And then for the proof, prover needs to generate the two key pairs with prime and one, SK prime, PK prime, which is the new key for the homomorphic signature. And this with the power one, I mean SK1 and PK1 is a signature, is a public key for the one-time signature. And then extend the statement with this way. And intuitively, you can see that the first part of OR can be run by a prover because he knows the witness, and the second one could be run by someone who knows the secret of the SK of the homomorphic signature. And then after generating a proof, prover needs to also do some additional work with sign the public key of the one-time signature by the secret key of the homomorphic signature, and then sign the proof also with the secret key of the one-time signature. Actually, this this guarantees the non-malleability of the proof or simulation simulation sum property of the proof. And later one can put this secret key of the homomorphic signature as a simulation trapdoor in a way that simulator, by having this, can pass the verification by generating a proof which satisfies the second part of it. I would say that this compiler can convert SNARK and Subversion SNARK to simulation extractable SNARK and simulation extractable Subversion SNARK. But this cannot support the updatable version. And in the next step, I'm one step before before constructing Lamusa, we needed to define a new notion of the signature. It's called updatable signature, which is inspired from the updatable CRS. And we defined two new algorithms called updating public key and verifying PK, which updating PK updates the public key and also provides proof of that update is done correctly. And this is the second algorithm just verify that the update is done correctly. And the idea here is that as long as one of the updating or generating the P public is honest, then one can sign the message by that. And as an example for such an updatable signature, you can think you can think as a schnorr in bilinear group and relying on BDH knowledge assumption, which just roughly speaking, BDH knowledge assumption says that, okay, if an algorithm generates as the input some generator of the group in bilinear group, and it's run and his random point tape, it can generate g to the power x and g 2 to the power x. Then the BDH assumption guarantees that there is an extractor who can generate x from by having the same input. So our Lamusa construction actually needed this updatable signature. Here is the slide about the Lamusa framework, which this framework actually taken in SNARK, as I mentioned before. It could be a standard or subversion or updatable SNARK, and then extend the language by the following you can see here. And by red color, again, I mean by W and SK is a secret key. They are per secret. For example, this is done by prover, this is done by similar for the code. And you can think that here we have to, one can look at this, look at it in a way that word is extended with the old word or the original word of the SNARK and with the new public key, and the witness also could be the original witness and this part actually. And the new CRS is extended by the new public key. Then one can just get a simulation extractable SNARK by if you use a SNARK as an input, and you can get subversion simulation extractable subversion SNARK if you use subversion SNARK as an input. And for updatable, if you use updatable SNARK as an input of this framework and use updatable signature, and so this public key should be the public key of the updatable signature, and CRS also should be the CRS of the updatable SNARK. Then it outputs a simulation extractable version of the updatable SNARK. And later we had we analyze our construction, I mean, both LaMusa and OCOCO with different tools and different, and analyze the compared. Yeah.
If you could look to wrap up now, that would be good.
Okay, I think I'm done, yeah.
Oh, okay. There was actually a question which I think is quite important earlier, which is saying that in our table of possibilities between updatability, subversion soundness, and subversion zero knowledge, where do transparent proof systems fit? So proof systems where the setup can be generated using a random oracle, for example.
Just a moment, I just, okay. Can you see my screen still? Okay. Could you please repeat your question, because for some moment I just missed everything. Yeah.
That was my question. If you go to the slide where it shows the possibility results for subversion, soundness, etc. Yes, that one. So where does transparent proof systems fit here?
What? Could you repeat again?
Where would transparent proof systems fit in here? Because intuitively, if you have a transparent proof system, then there's no trusted CRS that could be subverted.
Okay. I would say here, I mean, this actually, we say that subversion sound, having subversion soundness and subversion zero knowledge is impossible, but for the updatable case, we say that still there is a trust. How? Because there is a condition actually that verifier should update at least one of the at least one time the CRS, or the one who is trusted by the verifier should do the updating process at least one time. So this actually, I mean, this is not. I mean, in such a setting, I mean, in the updating case, we are not completely remove the trust, but it can be removed as long as verifier, for example, participate to the updating procedure, at least one. I'm not sure that
I mean, so you can argue that if you have an untrusted setup, then you don't need updatability.
For sure, yeah. Actually, this updatability, or I would say this subversion setting stuff, just is for the case when you have a setup that you need to make it with some trusted third party. Yeah.
Okay.
I think that the technical answer to this would be that the systems that do not have an explicit structured reference string live in a different model, because we know that in the standard model, zero knowledge proofs do not exist in non-interactive ones without a structured reference string, aka trusted setup.
Right.
So that different model can take different forms. It may be a random oracle model, which sort of assumes that the random oracle is perfect in a very strong sense, and therefore has all the magical properties that you would want, even without being updatable and without ever being subvertible. Or it may take the form of instantiation of that random oracle as concrete hash functions, in which case you end up making nearly tautological, nearly cyclical assumptions about the security of your scheme, saying that you're just assuming that it remains secure after the instantiation, and that assumption implicitly says that your underlying hash function has some sort of strong extractability properties that cannot be subverted and do not even need to be updated. So it sort of hides in there, and it's very difficult to analyze because these are indirect, sometimes cyclic assumptions. Conversely, they tend to rely on secret key rather than public key assumptions, so they may be more plausible. But technically, these are just different models, so there is also not carryover.
But maybe we can talk a bit about more practical aspects, both of simulation soundness and subversion security. So is the main point here to get provable security, or if you look at existing constructions that were not designed with these goals in mind, they actually have known security vulnerabilities?
Yes, actually. Here, the main goal is to get a provable security. Yeah. And that was the reason, actually.
But let's say that if you're happy with generic models, which are even worse than, let's say, generic bilinear groups, which are even worse than the random oracle model that Eran mentioned before, are things easier in this setting, or?
I don't know, actually, whether it is, I have no idea about this. Maybe Sebastian or Daniel, if they are here, maybe they can have some notes about it.
Maybe a comment I could make is that, yes, it's to get provable security, but you pay very little cost to get this provable security. So I think the relation to subversion soundness is very efficient. So,
and when you say provable security, how long are the assumptions under which the proof? If you have to state the assumption in a fully self-contained way with all the quantifiers, so it's provable under some assumption. My question is, where is this assumption stated, and how long is it?
It is provable in some. For example, in the case of the knowledge sound, it is provable in some non-falsible assumption, which is secure in, let's say, PBGM model, or yeah. I would say that, for example, in the case of the standard SNARK, actually, it is provable under some non-falsible assumption, which is secure in the GBGM model.
Okay, I'm going to start sharing my screen, and we can move on to some of our discussion topics. Okay. Thank you very much for giving the speech, Behzad.
Thank you.
Just a small note, if you're not speaking, please make sure you're muted. That way, whoever is speaking doesn't get the background noise and etc.
Can everyone see my screen?
Yes.
Yes.
Okay, we have some questions here, which we by no means have to stick to, but if there's sort of any consensus with which questions we want to start with there, because we probably don't have time to cover all of them. Okay, I'm just going to choose the first one then. What are the challenges to obtaining the what are the challenges in obtaining updatability for the OCOCO approach?
I was going to ask a question related to that. So what's the relation between UC security and simulation soundness?
Okay. Let's first start with the case of the CoCo actually proposed the framework to transfer any music to the to get a black box version of that SNARK in a way that it is UC secure. UC secure, and this actually they just added this black box extraction because now for as far as I know, for the UC secure, one cannot get this property relying on some non-falsible assumption or let's say knowledge assumption. And for some music, like as for example SNARK, since the soundness or knowledge soundness is based on some non-falsible assumption, so it cannot satisfy the UC security. To this end, the CoCo just added, first they added a black box extraction in a way that they just extended the proof by adding the encryption of the witness. Then in the UC security, the simulator of the UC can extract the witness by having the secret key of the public key that we generated already and put it in the CRS. So similar to now. What about the relation between the simulation extractability or let's say non-malleability of the proof and UC security? I'm not that expert in the UC security, but let me think, because I don't recall now what was the.
May I add something, Mary? Sorry.
Yeah.
Sorry, I am interrupting you. Maybe I can explain a little bit about it. I am Karim and have been just doing something about it. So Behzad also works in that. So maybe I would say that the reason is that in UC security, we need to simulate the corrupted parties. And in that session, as Mary already mentioned in the chat, we need to have black box extraction. And to have a black box extraction, the standard way we know that is just encrypting. But Subversion zero knowledge says that even if you have generated the parameters, you shouldn't be able to learn anything about the witnesses. But black box extraction says that if you have secret trapdoors of CRS, you should be able to extract a witness. So these two are introduction, and Belara in 2016 a little bit mentioned about it. And we cannot achieve Subversion zero knowledge plus black box extractability. Basically, we can achieve Updatable zero knowledge, which is slightly weaker than Subversion zero knowledge, because in Subversion zero knowledge, we assume that all setup is generated by a malicious guy. But in Updatable zero knowledge, we assume that one party is participated in the updating the elements. So basically, we can show that we can achieve black box extractability with Updatable zero knowledge. And we have done that work. Very soon it will come to ePrint. And but in that case, Behzad's construction achieves something stronger. They achieve Subversion zero knowledge, because in Subversion zero knowledge is stronger than Updatable zero knowledge. But if you want to achieve this black box extractability that CoCo original version achieves, so you cannot achieve Subversion zero knowledge because of this contradiction of the definitions.
You can sort of achieve something in between though, in the sense that you can have it so that your common reference string is either generated in a binding setting, which would be like your real world, how you actually generate it, or in a hiding setting, which would be in your simulated world, which would give you the sort of perfect zero knowledge. No, I've got those the wrong way around. But then you'd need to have some kind of assumption, assuming that you can't tell the difference. And precisely how you're going to do that at the same time as proving that you do actually know a trapdoor to the common reference string is, I think, possibly there's where the impossibility is.
Yeah.
Yes.
And you could move to the transparent setting more easily for this black box extraction. Makes sense. So it's quite easy to generate no one using a random oracle, while it's much harder for a structured reference string or system. Can people hear me?
Yeah.
Okay.
Yes, your sound was dropping out a little bit.
Yeah.
Okay, a quick question also. Can you see my notes? Because I can't see it on the shared screen, which is a bit worrying because I was taking notes.
I can't see it on my screen,
So
which is the one that's being shared, but maybe I'm on the wrong link.
That's strange. So how do I say? I was hacking away on Hackpad, but maybe I have to do something so it gets actually shared with people.
You should be able to just share the URL. You're giving edit access if you do that, but that's fine, I think.
Okay, I can. I'll post the URL then in the chat.
Mary, maybe try refreshing the page.
Oh yeah, also a good idea. Oh, there we go.
Okay,
at least one thing of notes.
But still the question that Yuval mentioned to me is not, because I am interested to know the answer, but his question was that what is the relation between this simulation extractability or let's say non-malleability of the proof with the UC security? I was thinking about it, but so far I have no answer, but I don't know, anyone can have any idea about it or not?
I'm glad it's a good question because yeah, it wasn't clear to me when I read papers on
my guess is that's equivalent. At least I want it to be equivalent. If it's not equivalent, then it's a bad definition.
I would say that the reason is that in 2006, Grot has shown that you can realize a black box simulation extractable NISC in a UC framework. Basically, you can realize the functionality that they have defined in 2016 if you have a black box simulation extractable NISC. This is the reason.
Oh. No, I mean, here, do we need to have exactly this simulation extractable property to get using it?
Yes, I mean, in some cases, it is shown that we don't need this strong simulation extractability. Okay. We can even go with just weak version, which adversary has allowed to query for true statements, not arbitrary statements. So
what paper is that in?
In 2006, in ZKProof Simulation Sound Practical by Grot.
Okay, thank you. Can we write that down in the notes?
Maybe I can.
I will refresh the notes again. Does my screen look similar to yours, Markov?
I think the notes are at the top, if I'm not
asking, yeah. Okay. So did someone add the link? Don't.
I can post it, yeah.
Is it this one? I hope I've got the right link there and I'm not just confusing people.
Okay.
I just shared the notes link so everybody can actually have them. I do think Dara, you shared something else, right? Just to make
sure. Yeah.
Also, I would note that about this question and regarding to the UC security. I mean, besides this simulation extractability property, I would say that, I mean, having UC secure subversion SNARK or UC secure updatable SNARK still is, I mean, unclear. Why? Because in the subversion sense or in the updatable sense, because we assume that there is no trusted party and the key or the common reference might be subverted. So for the zero knowledge proof, one needs to extract the trapdoor of the common reference string. And so this extraction rely on some non-falsifiable assumption usually. So I have no idea how one can, match this notion to the UC security when, for example, the simulator of the UC wants to generate the common reference string, and how one can simulate the subverted, let's say, CRS in the UC setting.
I would say that, okay, maybe I can add a comment about that. Yeah, exactly. Your question is a very good question. I mean, the idea behind Subversion zero knowledge and Updatable zero knowledge is using a knowledge assumption for extracting the trapdoors from setup and then using them in simulation. But as you mentioned, so if we have an updatable CRS, basically means that we have one honest party, but n-1 malicious party. So we can use this non-falsifiable assumption to extract the trapdoors from these guys, all of them. But the good point is that one of them is honest. So basically we can rely to some property and say that still no one can learn adversary to break the black box extractability because we have one honest. We have define these notions that tomorrow or the day after it will come up in ePrint. You will see, we call it tiramisu, continuing your work. So basically, there is exactly very good question that setup phase will not be UC secure, but the protocol itself will be black box extractable. So we, in technical answer is that you cannot realize the functionality of CRS generation, but you can realize the functionality of NISC. If you look at this paper that just Dario shared, Grot separated the functionality of CRS from functionality of NISC. And it's natural because in random oracle model, we don't have this functionality of CRS. So it makes sense to separate them. And in our construction, we show that we can realize the functionality of NISCs. Basically, NISCs would be UC secure, but we wouldn't have UC secure setup phase, but we will have a trustless setup for SNARKs.
And it's the NISC that you want to be UC secure because that's what you're going to compose in the more complicated protocol.
Yes, exactly. We have discussed about it that this is a trade-off. If you want to have a UC secure setup and UC secure NISC, so basically you have a trusted party. But using this updatable that Mary and Grot, they proposed, so we can basically have a trade-off that we will have a non-UC secure setup, but we will have a UC secure NISC. So especially in how can GGS and this is smart contract systems and Ouroboros, Philips, they use UC secure SNARKs. So basically we would say that you can ignore the trust in this setup phase of these protocols, but you will have a UC secure NISC.
I also feel that assuming a short random CRS to prove the setup in the UC setting is also not a bad trade-off, I would say. So relying kind of on transparency to get the to prove the setup, but then use the updatable thing to use the most efficient SNARK. I think the main problem with transparent proofs is that at the moment, at least as far as I know, they're still not as fast as Gross 16 or other updatables.
Is this also true for prover running time or only for verification? That's certainly the case, but for on the prover side?
I think Gross 16 is pretty good on the prover side as well, actually.
For transparent systems, I may be biased, I'm a co-author of Halo, but Halo is pretty fast for proving.
And Halo is what? Sorry for...
Halo is, it's designed for recursive, for efficient recursion, but it's a transparent proof system. It's sort of derived from Sonic and bulletproofs, kind of.
Sure, no, but my question is about comparing the two, not about like fast, it's fine, not fast, but if you look at, you know, I guess it depends on the type of computation and so on, but okay, I guess that's a topic for a separate discussion, but it's not clear to me how the things compare to each other and the different moving.
So the ideas that are making recent proving systems like Plonk fast and so reducing the gate counts for the same circuit, they can be applied to transparent systems.
Okay. Another kind of basic question, I'm not sure how we're doing in terms of time, because we're talking about all these notions of provable security, which are of course important, but I have a more basic question in terms of, let's look at the dream notion of security without, say, a random oracle. There is this issue of programmability of the CRS, right? And programmability is a violation of the real ideal philosophy. The real ideal philosophy says that whatever the adversary can achieve in the real world, it could have achieved in the ideal world. But in the real world, there is this CRS up in the sky that everybody can see. And in the ideal world, we're allowing the simulator to make up its own CRS, right? So we're not telling the simulator, here's a CRS, deal with it. We're allowing the simulator, hey, make up your own CRS. And this manifests itself in actual issues, like in real zero knowledge, you cannot transfer the proof, right? That's the basic story we tell our students, you know, when we explain zero knowledge. It's a proof you cannot transfer to somebody else. And, you know, so it's not, there's a deniability issue. So my question is, this is some kind of philosophical flaw. You can get around it in the interactive setting, but in the non-interactive setting, you know, again, I'm not saying it's a practical issue for the applications people have in mind, but I'm saying that at the philosophical level, there is an issue here. And it surely radiates to all of the more refined notions of security that have been discussed here. So my question is, what's your take on it as people who kind of deploy zero knowledge or develop it?
So I'm not sure I understand the point, because to my view, there is no CRS in the ideal world. The only place it exists is in the mind of the simulator. So
no, but there is in the ideal world. So let's think of zero knowledge textbook definition, the original definition that you know, it's non-transferable. The way zero knowledge was originally motivated, I have a proof that no one can claim it. Okay, and this is true because you can really simulate from scratch. But here, in the non-interactive setting, you have this CRS, and you're telling the simulator you're allowed to pretend that you can make the CRS, right? So you're changing, you know, I want to say that everything the adversary can achieve in the real world, it could have achieved in an ideal world. Again, there is this old paper of Raphael Pass that points to the deniability issue, and the related issue is transferability. Transferability can be a plus, but if you look at the pure zero knowledge, right? If you have a trusted party that tells you, hey, this statement is correct, I check the witness, it's non-transferable, right? That's real zero knowledge. If you look at an interactive protocol.
So when you're designing real-world protocols, you certainly have to take into account that proofs are transferable. I mean, that's maybe a third of the complexity of Zcash sapling is due to that, because we have to make transactions non-malleable, and we do that outside the proof system.
Sure. The question is how this fits into the modeling, because if we think of zero knowledge as a substitute, as you know, a trusted hardware that checks the witness and spits out accept, reject, then there is a fundamental difference between the notion of zero knowledge we achieve in the CRS model and this ideal notion of zero knowledge. And my question is, yes, so you're saying, yes, you're aware of it, I'm sure you are, and you're dealing with it. My question is, how does the modeling take care of it?
I mean, my take would be that we almost always have our security notions boil down at some point to, if you have a transparent setup, so something where you have a good source of randomness and your parameters are generated randomly, then you can't sort of, well, break things. So I think on a theoretical level, the problem probably is boiling back down to this whole random oracle programmability thing, not really being so possible in the UC setting. Because our simulator would be able to program the oracle is the thing in the NISIC setting.
I mean, there are some results in the global random oracle model, but yeah, I would have to, that would be one way of doing it, but again, only for transparent proof systems, maybe. One question I have, maybe a follow-up question. So the NISIC functionality, it allows everyone to verify proofs. So maybe in that sense, this means that proofs are transferable, also in the ideal world.
Yeah, this is why real zero knowledge does not exist non-interactively. It's only an augmented version, which is good enough for most practical. Again, it's a very delicate issue, because if you think of zero knowledge as an ideal functionality using a trusted party, it is non-transferable. And again, transferability can be a feature if you want it.
But non-interactive zero knowledge, as we model it using an ideal functionality, is transferable.
Yes.
Because you model something you model something you can realize, but if you have non-interactive zero knowledge using a trusted party, then you can model it in a way that's non-transferable. So if you have a non-transferable zero knowledge, you can use it to build transferable zero knowledge, but not the other way around. So non-transferable, again, if you want to prove a claim, a theorem so that nobody can claim it, this was the original motivation for zero knowledge. Yes, you can do it. Just saying that philosophically, there is not just philosophically, also practically from the point of view of deniability and transferability, there is some discrepancy between the ideal notion of zero knowledge and the thing we can realize non-interactively.
Okay, but I think,
okay, I think we need to wrap up now and move on to the next topic. Yeah. Sorry. Over to Yuval.
Okay.
So I guess this is the end of this discussion, right, Yao and Mary? I mean, the end per time, not in terms
per
of
time. Definitely, we could keep going on this topic for hours, I think.
Yeah, so by the way, feel free to keep discussing on the work group. There is a document that can be further extended offline. That's the intention of these working groups.
I do think the current state of knowledge is unsatisfactory here, because I mean, protocol designers don't really know to what extent they're missing something by not using these stronger properties like simulation soundness, and that is something that the standard will need to talk about.
Right. I definitely think that as a systematization of knowledge, this document should be extensive in the definitions that should be agreed upon by the working group and the community. So maybe that's one direction to extend, as well as capturing all of these ideas that were discussed here. And as Dara said, both from a theoretical context and how does that translate to the practical situation, right? So yeah, but definitely encourage everyone to join and contribute. I think this is the point of all these working groups. We will hopefully add these the next versions of this SoK to the reference document. And yeah, I'm going to stop recording now, unless anybody else has anything last to say about this topic for now. Okay.
Probably not.